Okay, so this is the third lecture on the strong CP problem. And today we're going to focus mainly on axions and various aspects of axions. Okay, in particular, we'll focus on axion detection. We'll talk about axion as dark matter and axion cosmology. Okay, and we're going to talk a little bit about why one may or one might believe that this is a reasonable solution or not. Okay, so we're going to talk a little bit about something I'm going to call the quality of the axion, and we're going to ask how reasonable this whole story is. Okay, so just to remind you of a few things we wrote down last time, we wrote down a couple axion models, but I wanted to remind you of a result we had, which we had. So we had a basic formula for the axion mass. Ma was equal to 0.6 milli-eV. Okay, so this is in GeV units, this is 10 to the minus 12, okay, times 10 to the 10th GeV, which is going to be a kind. This is going to be a kind of benchmark number that we'll use, divided by Fa. Okay, so remember, I guess going back even a step earlier, we said that the way we introduced the axion was we replaced theta by theta minus A over Fa. Okay, where if think of A as a canonical field, okay, a field of dimension 1, Fa is a parameter with dimensions of mass. Okay, this A over Fa is dimensionless. It's like the theta angle. Okay, and so this is sort of the basic formula we wrote. And you see this number can be quite small, and it's perhaps worth understanding kind of how we might get a formula for this. And one of the things I talked about in the very beginning was how in QCD the quarks condense. Okay, so what we said is that Q bar Q with some flavor indices was some number, let me just call it lambda cubed, sort of like the QCD scale, delta FF prime. Okay, so that was a basic expression we wrote. It's something that's a basic part of our understanding of QCD. And we can rewrite this a little more, in a little more instructive way if we have some background. If we have some background pion fields, I'm going to do the case here. Here last time in the beginning we did Q equals UDS. I'm just going to take Q equals UD. Okay, just because it'll make the algebra a little easier. Okay, so we'll just consider two light flavors. Okay, so in this case, what we write is Q bar Q is typically we might write as some dimensionless parameter lambda cubed U, where U is a unitary matrix, and U is e to the I pi. These are the pion fields dot tau, the Pauli matrices, divided by twice F pi. Okay, so we write an expression like that. Okay, and in terms of this, we write then the Lagrangian, the mass term in the Lagrangian, the term that violates the symmetry and gives rise to a potential for the pi mesons, okay, is the mass term, is the quark mass term. I'll write it Lm, is MQ, Q bar Q, where this is summed over flavor indices, okay, and this is just trace MQ U times this lambda cubed. Okay, so sort of 3/4 of physics of the 1960s, including a lot of things which happened here, okay, was just kind of working out the consequences of this for low energy experiments involving pions, K mesons, and so on. Okay, but what we want to, and in particular, if I expand this, I'm going to get a formula. If I expand to quadratic order in the pion fields, I'm going to get a formula that's going to roughly read m pi squared f pi squared is something like lambda cubed. Let's see, I've got mq. And I should write this as mu plus md. Okay, I'll go a formula like this, and again, I'm not guaranteeing you factors of 2. Okay, but this is such an easy exercise. If you've never done it, you should do it. Okay, so this is a kind of way of understanding the pion fields. Now, in the presence of a theta, okay, what happens here is this MQ has a theta term in it. MQ now has a phase. Just to, again, be a little bit schematic, I'll let you work out the indices. Okay? And now I have this MQ with an e to the I theta. Okay, so as I said here, if I work out the potential from this Lagrangian to second order in the pion fields, I'll get an expression for the pion masses, which looks like something like this. Now, in the presence of this theta, I have a term, when I expand the potential in powers of the pion field, I have a term linear in the pi naught. So now the potential has a term linear in pi naught. Okay, and if I can find it. Okay, so it looks like, in fact, let me write out what this is. So not to be so mysterious, V of pi, I'll just write the potential for the pi naught and with theta, and this is something that looks like lambda cubed, okay, and it's mu cosine theta plus pi naught over f pi, over 2f pi, minus md, I'm sorry, plus md theta cosine theta minus pi naught over 2f pi. Okay, so I have just taking that potential, that trace, and writing it out in terms of the fields. Okay, and then if I expand to second order, if I minimize the potential, okay, I find that pi naught, which I hopefully have on the next page here, yes, is twice f pi over mu plus md times mu minus md times theta. Okay, so I have so the pi 0, instead of being minimized at 0, is minimized at some non-zero value. And remember that the pions are CP odd fields, they're pseudoscalar mesons. Okay, so that's consistent with the fact that theta violates CP. Okay, and if I take this and I substitute back, okay, I get that V equals lambda cubed over 2 theta squared 4 mu md over mu plus md. And this is one of these somewhat mysterious sort of formulas I wrote down in a couple of the other lectures. And I just write this, all these things that involve ratios of quark masses and things like that. They're not that mysterious. Okay? They really come from rather simple exercises like this. Okay? And what we've done here, if you think about in the language of integrating out, remember theta is my axion field. Okay, so up there someplace, I have theta is like A over FA. So A is theta FA, essentially. Okay? And so what I've written here is a potential for the axion, which is some lambda cubed over 2 theta squared, all this other stuff. And then I have, I'm sorry, not A theta squared. I want to write this as A squared over FA squared times this other stuff. Okay? And the other thing I can do here is I can identify this lambda cubed in terms of the pi mass of the pi meson. Okay? And so that gives this formula I wrote last time, so this gives a formula which basically says that ma squared is equal to m pi squared f pi squared mu md over mu plus md and divided by fa squared. Okay. So it's a formula totally in terms of measured quantities, and it's valid up to terms that are suppressed by powers of quark masses divided by QCD scale. Okay. So this is something. So it's something we have a good handle on. We know a lot about the properties of this particle. Okay? And I say that translates into that formula I wrote up here, okay, for the Axion mass, being more careful, or being careful, I should say, about factors of 2. Okay? So let's see. I'm going to let's put this up a little further. Okay. So this is one, so the Axion mass is one of its basic properties. Okay, another set of things we might ask about are its interactions. Okay, and when I talked last time, I focused on 2 couplings. I focused on the coupling to F mu nu dual, either the FF dual of QCD or the FF dual of electromagnetism, and on Yukawa couplings to the electrons. Let me focus on this FF dual coupling. Where now, just to confuse the issue, F mu nu is the F mu nu of electricity and magnetism. Okay, so the first thing I'm going to ask is, how does this axion decay? And again, I want to think, we're going to think of it in this terms of this Fa of order 10 to the 10th GeV or larger. So the axion is very light. Okay, basically the only things it can decay to are photons, given what we know about neutrinos, in fact. Okay, so we can ask, one question we could ask is, how does the axion decay? Okay, so we have this coupling axion FF dual. In general, the coefficient here, there's some 32 pi squared, and there's some numerical coefficient, which I defined last time. Not too worried about it. I just want to get a sort of sense of orders of magnitude here. So let's ask how the axion decays. So we can draw a Feynman diagram here using this coupling axion to 2 gammas. Okay. And if we think about the lifetime gamma is going to be of order, well, it's going to have, let's see, I've left out the Fa. That's important. Okay. So the lifetime has a factor of 1 over Fa squared. Okay, or the inverse lifetime, the width. Okay, and the width has dimensions of mass, so just on dimensional grounds, the rest of that's going to be made up by ma cubed. Okay, and basically this factor is of 16 pi squared. This is coming from, you can think of this as coming from an anomaly diagram. We have our Pache-Quinn current, couples to some fermions and a pair of photons. So this thing is like alpha over 4 pi, and then in the rate it's squared. So we have an alpha over 4 pi squared. We can throw in another 4 pi for good measure for some phase space. Okay. Okay, and this is the lifetime. So let's think in terms of that 10 to the 10th GeV benchmark I used. So 10 to the 10th GeV, this was milli-eV, or 10 to the minus 12. So this is like 10 to the minus 36 times 10 to the minus 20. So that's like 10 to the minus 56. Okay, this number is, let's call this 10 to the minus 7. Okay, so this is something like 10 to the minus 63. Okay, and I should write this scales with ma squared. The thing to remember about ma is ma scales like fa, like 1 over fa. Okay, so this whole thing scales like this 10 to the 10th GeV over Fa to the 5th. Okay, so the width gets smaller, the lifetime gets longer as we make Fa bigger, like 5 powers of Fa. Okay, and see that? Okay, and I hope I did that arithmetic right. You should yell at me if I've done my arithmetic wrong, but I think that's right. So that's about 10 to the minus, just make sure I got that right. 10 to, let's see, this was EV, that was 10 to the minus 12, 10 to the minus 36, 56. I think this is wrong, actually. Oh, no, that's right. No, that was right. Okay, so 10 to the minus 63. This is in GeV units. A GeV is sort of like 10 to the minus 23 inverse seconds. Okay, so this is like 10 to the 40th seconds times this number 10 to the 10th over FA to the minus 5 as a lifetime. Okay? Okay, so this is kind of in the spirit of some of the things Neil talked about this week. Okay, this is in the spirit. This is, it's not exactly a symmetry. We don't have like a Z2 or something that's accounting for this lifetime. Okay, just the dynamical structure of this thing, its couplings and so on, ensure that this lifetime is enormous. Okay, the age of the universe is about 10 to the 15 years, or about 10 to the 22, 10 to the 23 seconds. So this is much, much longer than the age of the universe, and that's the case even if I decrease FA and make the axion somewhat heavier, okay, down to rather somewhat small FA. Okay, so these are some basic properties of the axion. Okay, so what are the consequences of this axion? Okay, so let's pull this out. I should say, when Pache and Quinn made their proposal, okay, they were imagining FA was like 100 GeV, sort of something around the weak scale. At 100 GeV, if we look at that formula, I think I can still read it, right? The lifetime then is kind of order seconds, okay? So if you have a beam and you crash a beam into you take your whole beam, this is kind of the experiments people did, crash it into a target, okay? Then we'll have a big, long pile, let's think of a kilometer of Earth after the collision, and you look for photons from these axions. You assume that you produce axions, and you look for photons from these axion decays. With a kilometer, sort of a part in 10 to the 5th or so will decay before they reach your detector, and you can hope to see them. And the original Pache and Quinn idea was ruled out rather quickly. Okay? In fact, one knew that this axion decay constant had to be rather large. Okay? And once the axion becomes light enough, so once the axion is fractions of an EV or so, they can be produced in stars. Okay, so, and basically I can draw this triangle diagram I can draw in reverse. Okay, so for example, I can have two photons in a star collide, producing an axion. Okay, so using this axion-FF dual coupling in reverse. Okay, and this axion interacts quite weakly. It interacts at rates that are suppressed by this 1 over FA. Okay, so the axions escape the star. Okay, and if you produce too many of them, you just kind of burn up the star in axions. Okay, so let's see if I like this formula. Okay, so a kind of formula for this is, for example, in the sun, the luminosity in axions, LA, is this coupling to two photons. I'm writing it slightly differently. I defined it last time, GA gamma gamma squared. It's essentially this coefficient of FF dual times 1.85 times 10 to the 17th times the solar luminosity. Okay, so unless this coupling GA gamma gamma is very small, you have to sort of beat this 10 to the 17th. Unless that coupling is very small, you have to the star will burn out quickly. Okay, and what this translates is into a limit that FA, okay, is greater than of order about 10 to the 9th GeV. Okay, so it's kind of that ballpark I used there. Okay, The precise limit depends on which astrophysical processes you look at, and I'm not going to review those here, but these include things like the strongest limits come from things like red giants, supernova 1987A, okay, globular clusters, okay, various sorts of limits, and they're kind of all in this ballpark, some slightly stronger than others. Okay, but there's a lower limit on this Axion decay constant. Okay, so it can't be just anything we want. Okay, we have a constraint at that end. Okay. All right. So this is so I've kind of finished what I intended to do last time. Okay, and so let me tell you what I'd like to do in the rest of today. Okay, so I can do that here. Oops. Okay, so this is our lecture 3, and what we're going to do, hopefully, is we'll talk about cosmology of axions, and axions as dark matter. And I'm going to call this conventional. Okay, then I'm going to talk a little bit about axion detection. And one is dependent on the other. Okay, because when we talk about axion detection, I've already sort of told you we can't detect axions in accelerators, okay, or in kind of conventional, we can't produce them in numbers that we could hope to see them. But what we mean here is detecting axions as the dark matter. Okay, so the axions would be around us, and that requires we kind of resolve first this question of how the axions were produced. Okay. Then I'm going to, then I talk about something I'm going to call the problem of axion quality. Okay. And I want to use kind of quality in a technical sense, and I kind of have in mind also axion detection experiments where you talk about cavities in their queue. Okay. And here the question is, we've already sort of alluded to, we've sort of made a rather weird proposal. Okay, we said, we're going to impose this global symmetry. Okay, and first of all, we're kind of all by now mostly pretty allergic to global symmetries. And then this global symmetry has to be a really, really good symmetry, but not a perfect symmetry. It's got to be violated by QCD. Okay, and whatever else violates it better be smaller than that. And we'll kind of be quantitative about that, and we'll see that this is somewhat problematic. Okay, it really does call in something serious. We have to ask about whether this whole set of ideas is viable. And so having done that, we're going to kind of widen our view of how axions might arise. I mean, I showed you two models, this DSFZ and NSVZ model. And we're going to sort of enlarge the kind of space of possibilities. So we'll, in particular, I'm going to mention axions in string theory. And having done that, we're going to sort of change the rules a bit, and we're going to talk about axions in unconventional cosmologies. And I hope this will be a lead-in to some of the things you'll hear about from Peter Graham next week. Okay, so good. All right, so let's talk a little bit about Axion cosmology, and we already heard a little bit from Neil this week about how such a cosmology might look in the framework of sort of coherent behavior of fields. Okay, so let's think a little bit about this axion in the early universe. Okay, so if we think about, first question is kind of what's it doing? Okay, so the axion mass. Let's think about, in some sense, this 10 to the 11th or 10 to the 9th GeV number is a little weird. Okay, it's not a kind of natural number, maybe, which we would pick out from things we know. And we might have said, let's talk about the Planck scale or the unification scale or some large scale. So let's think about FA as 10 to the 16 GeV for a moment. Some kind of unification scale. Let's think how heavy the axion would be, right? So the axion MA, right, was like this m pi squared f, m pi f pi. So that's like 0.01 GeV squared. I'm just rederiving this formula. Divided by 10 to the 16th GeV. Right, so this is pretty light. This is about 10 to the minus 18 GeV. Okay. Okay, so in the early universe, okay, this is extremely small. Okay, so we could ask, when is h 10 to the minus 18 GeV? Okay, so we could ask, for example, for what temperature is it 10 to the minus 18 GeV? And remember, as Neil taught you, h is like t squared over m Planck up to some g factor and so on, which he told you generally don't have to worry about, so that he freed me up for never having to keep track of it. And so this corresponds to t of like 1 GeV. Okay. So what that means is when the universe was hotter than a GeV, assuming it was hotter than a GeV, okay, then the axion potential was of no importance. Okay, the axion did whatever it did. Okay, and so the axion initial value, if you like, let's call it A naught, or A of some T naught, is undetermined. I should put a question mark here. Okay, just, right, whatever potential there was is presumably of no importance. Okay, and so now the question is, should we think about an axion at T naught? And we've heard a little bit about inflation in these lectures, and if we had a period of inflation, okay, then we would say that the axion would be, we would expect the axion would be uniform. So A of T naught would be a number after inflation. Fixed after inflation, at least in our observable universe. Okay. So we could ask, what happens to it? Okay. So the first thing you might worry about is, well, maybe CP is violated, but eventually this axion is going to settle down into its potential. It's going to do something. So we've sort of got a picture like this. Okay, so if I think of my potential for the axion, here's A. Okay, so I have something kind of looks like this. Okay, the 0 is kind of special. The 0 is the point where CP is conserved, so the origin in this A space is meaningful. But basically, we're going to start out at some point here, A naught. Okay, the curve doesn't really look like this until the universe gets to be rather old. Okay, initially, the potential is almost flat compared to any relevant scale in cosmology. Okay, and Neil told you what equation this field obeys. It obeys an equation which looks like this: A double prime plus, and let's here put V prime of A equals 0. But it also has a friction term coming from the expansion 3H A dot. Okay, so this is the equation for this field if it's a homogeneous field in the early universe. Okay, and what this field does, it basically is this system is overdamped. Okay, so for H, when H is much greater than MA, okay, and we've seen that this might be rather late. Of course, you can plug in other numbers here, and we will, but this will be, perhaps rather late after inflation. It's overdamped for a while, and in that case, the field is basically just sits still. So A dot's approximately 0, okay, And then when h is less than of order ma, the field starts to oscillate in this potential. So it oscillates, and its motion damps out. Okay, so it oscillates. As it oscillates, it looks basically like a system, a collection of particles. It's like a dense collection of axions, all with zero momentum. Okay, it oscillates like this. The damping slowly kills off this oscillation. Okay, there would be other damping terms. I could also put, for example, a gamma a dot. This gamma would be just the inverse lifetime of the axion, but we saw that number is really long compared to any time scale we care about. Okay, so we can forget about that. Okay, and Neil told you a little bit about the solutions of this equation. Let me just leave you as a little exercise. It's really easy. If you take A of t to be equal to some slowly varying function for this region, f of t cosine mat. Okay, so I'm just keeping the quadratic term in this potential. If I take the potential in this form, if I take a solution in this form, it's easy to check that f of t is equal to t naught over t, some reference time t naught over t to the 3/2 for radiation domination and t naught over t for matter. And what this corresponds to in both cases is the dilution, as Neil talked about, the dilution of the density by the expansion. So basically, if too many a's here, but if a of t is the scale factor, then this is what's happening here is that we're damping out like a of t cubed or like the temperature cubed. Okay, so we're going like the temperature goes like the inverse of the scale factor. Okay, so that's something rather easy to check. You just plug this into the equation, write a first order equation for f and solve it. Okay, okay, so that gives you this expansion. Okay, now, all right. So now the question is sort of what happens. So we have this thing. It sort of starts out maybe not in the right place. Then gradually it settles into its minimum. Okay, but it keeps doing this oscillation. Okay, it keeps looking like matter. Okay, and that's a potentially, well, a problem or a bonanza. So let's think about that a moment. So when the axion starts to oscillate, when h is like 1 over t, is of order ma, okay? And if I ask what fraction of the energy density is stored in axions at that point, well, okay, the energy in axions is ma squared fa squared. So let me call that rho A. And I want to divide that by the energy density of the universe. So I'll call that rho total. And that's h squared of order h squared mp squared. Okay. The great thing, I think, again, as Neil said, the great thing is you can kind of not worry too much about factors of 2 and g star and so on, and you usually get pretty close to the right answer. Okay. So this ratio, h is like ma, so this is like fa squared over mp squared. Okay? So the fraction of energy in axions initially is small if fa is small. It gets larger as fa is larger. Okay? And then, though, the axions dilute like 1 over t cubed. Okay, they got like T cubed, I'm sorry. As the temperature gets lower, they dilute like T cubed, but the radiation dilutes like T to the fourth. Okay? So eventually, the axions win. Okay, so when is that? Okay, well, or what's the worry? Okay, one worry would say is, well, you know that we learned that the matter radiation inequality should occur somewhere around a temperature of order an electron volt. Okay, so if T is of order an electron volt, so we started with T of order, for our little example, T was of order 10 to the 2 GeV. Okay, and now we're going to T equals 10 to the minus 9 GeV. Okay, so that's 11 orders of magnitude. Okay, and yet our initial energy density, our fraction of the energy density initially was like 10 to the minus 6. So this is bad. Okay, by the time we get to what would have been matter radiation inequality, we are all matter. Okay, and in fact we can turn this around. And if you put in these numbers, if I change, let's see, was my 10 to the 16th here? Yeah, let's change my 10 to the 16th to 10 to the 11th. So if I put 10 to the 11th, okay, then H is, H is, I got to get my numbers right here. Okay, H is 10 to the minus 13. This is, H is 10 to the, I got this right, 10 to the minus 13, yeah. Okay, so this corresponds to a lower temperature, and I'm not going to get this number right, unfortunately. But when you do this estimate, you'll find that roughly you have matter radiation equality for FA around 10 to the 11th, okay, at an EV. Okay, so there's some constraint. We have two constraints. We have this constraint from stars, okay, and we have a constraint from cosmology now, which is bounding the axion decay constant in a particular range. It's not that broad. I'm being kind of rough here. We're going to improve this a little bit in a moment. Okay, but we have some range. And at the high end here, the axions will be the dark matter. So this is, okay, you could say, where did that scale come from? Okay, is that, I have to think about models and tuning or what have you, but at least but this is, perhaps not, at this stage, not better or worse than sort of things we've talked about up to now.
Are you taking an initial temperature for the axions? Or like in general, they're decoupled, right?
Right. No, so I'm just taking the axion as a coherent field, okay? So there's just a field, it's essentially zero temperature. Okay, when I solve this equation, I assume the axion was constant. So I assume the axion was homogeneous. Okay, there are, I'll say a little bit more about this assumption. You certainly can produce axions through thermal processes. You can also produce, depending what your assumptions are about the history of the universe, you can produce them through, by producing strings, domain walls, other objects. Okay, so there are a number of uncertainties in this estimate, okay, which depend on your assumptions about cosmic history. Okay. Any other questions? Okay, so I hope you come away from the feeling that even if I don't get the calculations quite right, you can go home and do a better job on them than me. Okay, so good. So let's think a little bit about improving this estimate. What are some of the things we would need to do to improve this estimate? Okay. So one thing I've left out so far is that this axion potential depends rather strongly on the temperature. In fact, it depends quite strongly on the temperature. This here. Okay. And actually, discussing this is one of the several reasons I went through in the first lecture, a bit of this discussion of instantons. Okay. And I told you that we couldn't really compute the theta dependence in QCD using instantons. And that's true at 0 temperature. Okay, that calculation was basically a strong coupling calculation. We didn't have control over it. But at high temperature, things are different. So at high temperature, with some caveats, so I'll put a little star here, okay? The equilibrium thermodynamics of QCD is controlled by g squared of t, the gauge coupling at the scale t, okay? So what does that mean for this calculation of the axion potential? So at 0 temperature, remember we thought about instantons, and I drew them as a kind of blob. Okay? And out of this blob came the various light quarks, the 0 modes associated with the various light quarks. And I'm thinking about 3 light quarks still. So I have U bar, D bar, S bar. And what I had was a calculation that looked like something like this. It looked like mu, md, ms. That was because I had to use the quark masses to close up these various 0 modes. Okay. And then I had various stuff, but in particular I had an integral d rho. Okay. I had a lambda, I should say, lambda to the b naught. So b naught, remember, this lowest order beta function, a useful formula to remember. This is 11/3 Ca minus 2/3 times the number of fermions in the fundamental. Okay, so for QCD, Ca is 3, so this is 11, and with 3 flavors, this is 11 minus 2, which is 9. Okay, so I have lambda to the 9th. So I'm going to call this F because I'm going to really imagine computing the free energy now as a function of theta and t. Okay. I should actually remember also I've got something like cosine of theta. Okay, theta again is now my axion field. It's my A over Fa. Cosine theta, and then I had this nasty rho integral to do. So I had d rho. And rho, and basically I can figure out the rho on dimensional grounds. This has dimensions of mass to the 4th. Here I've got 9, 10, 11, 12. So I need rho to the 7th. Okay? And again, this was badly divergent for large rho, but not anymore. At finite temperature, this cuts off roughly as exponent minus pi squared rho squared t squared. Okay, so basically temperature is another scale. Okay, and it enters this calculation, okay, in a way that cuts off the large rho behavior. Okay? So this thing actually behaves like lambda to the 9th, mu, md, ms, divided by t to the 8th. So those are those masses that those are those masses which I told you about at the very beginning. So the mu is like 2 MeV. We should correct, well, there are various things I should be careful about. Okay, there are temperature corrections, but those are small and logarithmic. I have to be careful also about specifying the scale. Okay, the renormalization scale and mapping onto those numbers I gave. Right now I'm being a little bit schematic. I'm really pretty much focused on this t to the 8th. Okay. But this computation is known, is none. So the full computation was done, all kinds of things happened in Princeton. It was done in Princeton, but at the university, by Gross, Pisarsky, and Yaffe. And this is described in a beautiful article in Reviews of Modern Physics from about 1980 or 81. So I'm sorry, I didn't look up the reference. Okay. But there's a very nice pedagogical discussion of this and quite detailed computation, including doing the renormalization carefully, okay, and carefully evaluating the determinant that's required here. Okay. So anyway, but I say I want to really sort of stress this. I want to stress this rapid fall off. So let's see. Yeah, my picture is still up there. Okay. So in terms of my picture, what this sort of says is the potential for the axion. So again, think of this theta as A over FA. Okay. This says that the potential for the axion, okay, actually sort of turns off quite rapidly at high temperature. Okay, and so you have to do all of this a little more carefully. Okay, and I think what I'm going to do, let's see, so we don't lose all our time, let me just say a couple things about this, but I'm not going to, yeah. All right, let's say a little bit more. I think we have time for, except I probably erased the equation. No, I didn't erase the equation. So if I go back to this equation, okay, what I should put here for this v prime of A, okay, I should have some ma squared as a function of temperature, okay, times A squared, times A. Okay, and so I need to solve that equation. Okay, and that turns out not to be that hard to do. Okay, let's put this over here. No, put this here. Okay. Okay, so this is sort of kind of at the level of the things that you can do with your undergraduate differential equations knowledge. Okay, so with this choice, it turns out you can get a good approximate solution if you consider something define an oscillation temperature T-os, where the thing starts to oscillate, is 3h of the T oscillation. So remember the h is a function of time, or I can think of it as a function of temperature. It's the Hubble parameter. Okay? And if I do that, I can solve this equation in an adiabatic approximation. And you find that rho, the density as a function of temperature, is rho at this oscillation temperature. And times r here is the scale factor, r cubed at the oscillation temperature over r cubed of t, times ma of t over ma of t oscillation. Okay. All right, so we get some refined version of that very rough calculation I did before. And I want to skip something, so let me just see if I can put a number in here. R is the scale factor. So R is sometimes A. And just because we've got A for the, because we have A for the axion, I wanted to use a different letter. Okay. Yeah, I'm sorry, I'm going to give you, well, yeah, okay. Yeah, okay, so I don't have this in a nice form, but let me write this in. So this gives h omega axion, I'm sorry, omega axion is, h is 0.957 times 8.29 times 10 to the minus 4 I don't like this. I'm sorry. This is not the formula, way I want to present this. Let me just tell you the answer. Okay. The result of this, okay, so we had this rough calculation before. In fact, the result of this is that one gets current omega axion is omega dark matter for Fa approximately equal 10 to the 12th GeV. Okay, so so that, all right, so that's sort of within an order of magnitude what we got before, but we have to be, as I say, careful about this temperature dependence. Okay. Now, there's been some controversy in the last couple of years about this computation, mostly coming, as I say, this is another complaint about lattice gauge theory, I guess. But there's been some controversy coming from lattice gauge computations where there have been arguments about this. Yeah, let me see if I can. Yeah, no, we're missing it. About this computation of the free energy. And I'm sorry, I'm missing a formula here. Once again, I got my notes out of order. Yeah, okay. So for example, okay, if you do this instanton computation, you take the result from Gross and Pisarsky and Yaffe, just to give you some kind of feeling for numbers, you find that the free energy d2f d theta squared of the free energy f of theta t at t equals 0, t equals 1.5 and theta equals 0 is 3.7 times 10 to the minus 14 GeV to the fourth. Okay, this is the small number. Okay, because of that, because already by the time we've gotten to 1.5 GeV, we've gotten a lot of suppression from those 8 powers of temperature. Okay, so you might have sort of naively thought the answer was of order these quark masses. So that's like 0.05 or something, 10 to the minus 5 rather. Times GeV to the fourth, but it's actually much smaller. Okay? But there's been some controversy about this number. Okay, I'll phrase it this way. It's actually phrased a little more generally. There's been some controversy about these numbers. Okay. Lattice results are kind of all over the map for this. And there have been claims, so differing by as much, I should say, as 5 orders of magnitude. Okay? And there are claims that, in fact, this old Gross-Pisarsky-Yaffe calculation is not reliable. It's subject to exponentially large errors. Okay? And I'm not going to sort of trace through all the reasons for that, but those arguments I claim are wrong. And so what I claim is that for large t, the semi-classical calculation should be reasonably accurate. Let's say it's reliable to the degree I do the calculation accurately. Okay. And it's also true that we know the zero temperature behavior. That's that Axion mass formula I wrote before. Okay. So what I claim is we know the asymptotic behavior of the free energy both for high temperature and low temperature. Okay? So what does that mean? That means that, well, what we don't know is what's in between. And when you look at this calculation, when you actually look at what the typical oscillation temperature is, it's a little low. So the typical, I didn't put any numbers here, but for example, for these kinds of numbers, the oscillation temperature is of order 0.7 to 0.9 GeV. Okay, it's in a regime where QCD is strongly coupled, and we can't really do reliable calculations. Okay? So a solution to this is to simply attempt to, or to allow for different interpolations between the expected high and low temperature behavior. Okay, and I'm not a terribly sophisticated experimental analyst, so for me that just means I draw some curve that goes between one or the other, draw a set of curves. Okay, and in particular, what you find is that for a broad range of interpolations, okay, omega Axion varies only by a few percent. So I'll call this lie less than about 5%. Okay. So I would claim, and as you look at some of this literature, I would claim that first of all, you shouldn't trust anybody who tells you that already at a few GeV, the lattice gives a result very different than the semi-classical calculation. Okay. And second, I'd say that given that one knows the asymptotic behavior, there's very little sensitivity, very weak sensitivity to the unknown effects of QCD in between. That's not to say it wouldn't be nice to make these calculations more precise, okay? But I think this is some guidance for what one's looking for. Okay, so.
So based on that instant computation, it looks like the axiom mass varies like 1 over t to the 4. That means if I plug back into the energy density, it looks like it does not behave like not matter anymore. So the dilution of
No, but this is only, so all this behaves, it's true, it doesn't behave like matter for temperatures kind of above the QCD phase transition, okay? But we're interested, I'm interested in, ultimately in this broad sweep. So we're sort of asking, what does the density look like just after the QCD phase, just after QCD has kind of settled down, okay? And this mass has become temperature independent, then what does it look like for over these what are microscopically eons between that temperature, okay, that temperature of order 100 MeV or 10 MeV perhaps or something, and a temperature of order in EB. Okay, other questions?
Again, in that instanton calculation, my understanding is that in those interactions, that every particle, every fermion charge under QCD should be coming into it.
Right.
Are there a lot of spectator lines that are just not drawn?
Well, effectively there are, but so you could ask what happened to the charm in the bottom and the top. Okay, and one way to say this is because they're these zero modes were not exact zero modes, right? Because what I used here, what this indicated was. What this little slash indicated was I do some perturbation theory on these eigenvalues, and they're raised by the quark masses. Okay, for the quarks that are heavy, they're heavy, say, compared to the QCD scale. Okay, I can just integrate those out from the start and absorb that into what I call the QCD coupling. So I'm interested. All the action in this problem is at these temperatures where, ultimately temperatures where my control over QCD isn't even really that great. But I'm kind of, again, sort of taking a benchmark a little below the charm quark mass. That was this 1.5 GeV I used, okay, as a kind of place to check these. Okay, and at that point I integrate out these other fields. They just get absorbed into redefinition of coupling. And if you like, they can also, if I was a hard worker, I could perhaps correct some higher dimension couplings and so on. But that's basically where those go gone. Okay, it's a good question. Any others? Okay. All right. So now we sort of have I think a robust picture of how we calculate this axion dark matter density, and now I want to think a little bit. Now having said that, we can ask, well, let's think about looking for axions, okay? And so we now kind of have an idea where to look. And the question is just whether I can look in my notes. Okay, so let's think how we would look for these axions. Okay, so we have, we know these days pretty well what the dark matter density is. This calculation tells us what the axion mass is. It tells us it's a few micro electron volts. Okay, and so now we want to look for these particles. Okay, so what might we do? Okay, well, we have various couplings at our disposal. The most promising is this FF dual coupling to electrodynamics. Okay, so we have this coupling AFF dual, okay, which is A E dot B. Okay, so one strategy, the most active strategy for looking at the present time for axions is to consider a large magnetic field in a cavity. Okay, so a large magnetic field in a cavity, in a high Q cavity, a superconducting cavity, okay, and basically what you look for is an axion in the dark matter coming in, okay, and converting into a photon through this coupling. So we have a background magnetic field. Okay, we have the axion, okay, which now sources a mode of the cavity. So now you go back to the things you learned in your graduate course about electromagnetic cavities. Okay, and you work out, okay, what is the rate, given this flux of axions, what is the rate for axion production. Okay, and what I actually just want to tell you is some of the parameters of these cavities. Here we go. What happened to my... Oh, here we go. Okay. All right, so the coupling here, this coupling of A gamma gamma, GA gamma gamma, is some number which is alpha, defined structure constant at quantity G gamma over pi FA. Okay, and G gamma is a number, typically it's minus 0.97 for this KSVZ model, and 0.36 for this DFSZ model. Okay, so there are various couplings you can compute. Okay, yeah, I still have lost a number. I wanted to tell you what these numbers were, but this B is of order 7 Tesla, and and Q is of order 10 to the 5. Unfortunately, I'm not finding these numbers, so it's kind of hand waving. But there's one now substantial experiment. Okay, this experiment is known as the ADMX experiment, for Axion dark matter experiment, and it's at the University of Washington. Okay, and this experiment has at this point excluded some of the parameter space of a good deal of the parameter space of the KSVZ model and some of the parameter space of the DSVZ model. So those are again these two sort of benchmarks, and so already at this point there are interesting exclusions. And over the next few years, the experiment will rule out or make a discovery in a wide swath of the parameter space. And again, I think you'll hear a lot more about this from Peter, but you can think about some of the things that are going to be the experimental issues. So, for example, in this, why do you want a large Q in the cavity? You want that because this axion, okay, has very small width, okay, and it has a mass and associated with that a frequency which you don't know well, okay, and which is small. So you need to be able to make small narrow steps in frequency, okay, and that's kind of the challenge here. The challenge, you can't just sort of turn it on and sweep quickly through a broad range of frequencies. Okay, so I have some pictures, but I think I'll save that for a lack of time. Okay, so. Something bad happened. Okay, so let me come back now to this whole idea, though. Okay, so this is good. We kind of understand a little bit what we're looking for. We understand how axions could play a significant role in cosmology and could be the dark matter. Okay, but let's go back to our initial set of assumptions and questions. This whole idea that the axion is this whole idea of the axion and this Pacheco-Quinn symmetry altogether. So, oftentimes when we learn quantum field theory, to make things simple, textbooks and so on will talk about global symmetries, but global symmetries are a little weird. I mean, we sort of think that physics is local, and in fact, we know that in theories of quantum gravity, there are no continuous global symmetries. This is something that is, at this point, almost a theorem. It certainly applies to broad classes of theories we know, to string theories in particular. Okay? So what are we talking about? Okay? But there are approximate global symmetries, continuous global symmetries we know in nature. Okay? Probably the most famous and important one is baryon number. Okay? So how many of you know why baryon number, where does baryon number come from? Why is baryon number a good global symmetry?
It's an accidental symmetry?
Yeah, it's an accident of?
The standard model.
It's an accident of the standard model, right? So in the standard model, I can't write down any operators of dimension 4. There just aren't any operators of dimension 4 which violate baryon number. The leading operators within the standard model which violate B are dimension 6. Okay? So if I say that those operators are generated by effects at some very high energy scale, like 10 to the 16 GeV or something, okay, they're not important. Okay? So baryon number is in fact an accident. Okay. So let's ask how we might get this Pacheco-Quinn symmetry as an accident. Okay, so what do I want? Let's make something very simple. Okay, so in this NSVZ model, for example, we had a scalar singlet. Okay, so we had a field phi. And let's just look at the potential. Okay, so what do I want? I want the potential to have a symmetry. Phi goes to some e to the I alpha phi, where phi alpha is a continuous variable. Okay, and so I want to forbid a lot of stuff in here. So I can have, for example, m squared phi squared, but I can't have mu squared phi squared. Okay, I can have phi to the lambda phi fourth, but I can't have lambda twiddle, let's call it, phi fourth. There are all sorts of things that have to be forbidden. Okay? So how could I do that without just imposing a symmetry? Well, one thing, a simple thing to do is to impose a discrete symmetry. So a lot of you have worked in supersymmetry, for example, and where you talk about an R-symmetry, which is some kind of discrete symmetry. And in this lore that we don't expect continuous global symmetries, discrete symmetries are okay. Okay. So I'll allow you to impose discrete symmetries. So we can impose a discrete symmetry that phi goes to e to the 2 pi I over some integer n times phi. Okay. And so if n, let's take n to be 3, for example, just as a warm-up. So for n equals 3, that gets rid of this, right? It gets rid of this. Let's put 6, actually. Bigger. Gets rid of this. It gets rid of phi cubed. Right? So it accounts for a lot of these terms I don't like. And the first term it allows is a pretty high dimension. Okay, so it would allow me a term that's like 1 over some mass scale, some maybe large mass scale phi 6 plus complex conjugate. And I probably should put a number here, a. Let's put some constant a, and I don't want to call it a. Need some other name for it. Let's call it just. Just to indicate that it actually might also violate CP. So in general, it might be a complex number. Okay, so that number is allowed. Okay, now, is that good enough? Okay, the answer is no. Okay, so how do we figure out what's good enough? What's the criteria? Okay, how good does this symmetry have to be? Okay, so what's the issue? It's a little like this thing I started out with where I minimized the potential for the pion field in terms of theta. Now I want to minimize the potential for the axion. Okay, so remember my phi is roughly f axion e to the I axion over fa. Okay, and what I want to make sure is I want to make sure that theta is small. So remember, theta has to be less than 10 to the minus 11. Something of that order. 10 to the minus 10, I guess. Let's call it 10 to the minus 10. Sorry. Theta less than 10 to the minus 10. Okay. So what do we want to, and what is that? That's expectation value of A over FA. Okay. So let's look at our potential here. Okay. This potential, if I treat this extra term, this 1 over m squared term, as a perturbation, okay, I'll first find a minimum for the axion potential at a equals 0. Equals 0. This coming from QCD. Okay, so this comes from the fact that I have this m pi squared, f pi squared over fa squared, a squared. That's the thing that's driving the axion to 0. Okay, so that gives rise to fa equals 0. But now, from this extra term, I have a term that's linear in A. So I have a term that goes like f a to the 6th over m squared. Let's see, I'm sorry, f a to the, get my dimensions right. I have the dimensions right. Yes. And then I have a, this mass fourth, a over fa. Okay, so I have a linear term in the potential for a. Okay, and what that's going to do, that's going to lead to a shift in a. Okay, or lead to a shift in a over fa. So a over fa is going to be of order the linear term here. Okay, which is fa to the 6th over m squared. Okay, and then I divide this by, and this gets divided by ma squared. Okay, and it turns out this is far too large. Okay, and in fact, it turns out that you have to forbid operators of much higher dimension. Okay, one needs this, when one does this calculation, one finds that one needs this z, this n rather, the n in this symmetry. So I've imposed here a Zn symmetry. I need n greater than of order about 12. Okay. So that's pretty weird. Okay. That's sort of a statement that, why should I have Z12? Who ordered that? Okay. And that sounds very, and that seems to be, though, the kind of thing I need to account for a Pacheco symmetry of the quality that's required, okay, to understand, to solve the strong CP problem. Okay? So this is a puzzle. It's a long-standing puzzle. It's something people recognize pretty much from the very beginning. Okay? That we have this kind of pretty solution, but hidden away here is this little scandal. Okay? That we need, that explaining really why this is such a good symmetry isn't easy. Okay? So what can one say about this? Okay? Well, perhaps one has to live with this. Perhaps maybe the idea just isn't a very good one. Okay, but in the early days of, I guess, what was called the first superstring revolution or something, Ed Witten made an observation about string theory and axions. Okay. So it turns out that axions and approximate Pacheco symmetries are pretty typical of string theories. Okay. So, and I think you're going to hear more about this from Nima, actually, in his talk today. So generically, these sorts of fields are generic. And what is their real defining property? The real defining property is they have some sort of exact periodicity. A goes to A plus 2 pi times some constant, which I can then call Fa. Okay, so, right, and what does that mean? Okay, well, the context in which people have largely thought about this is if I have supersymmetry or some approximate supersymmetry, and this doesn't need to be TeV scale supersymmetry for this purpose, but you can think more about what scales might be required. Okay, so if I have some approximate supersymmetry, the axion is part of a multiplet. Phi, which has some, let's call it rho plus IA. It has among its scalar fields, it has a complex scalar field. Okay. Something I can think of as a real or non-compact field rho, and this compact field with 2 pi periodicity A. Okay? And then what sort of potential, or let's think of superpotential, do you have for this phi? Let's write W phi. Okay, so W phi has to be an analytic function of phi with this periodicity. Okay? So it's of the form a sum e to the minus n rho plus IA with some coefficient Cn, okay? Like we learned in our first course in Fourier series, right? So we have something with this structure, okay? And now, provided that rho is reasonably large, okay, these terms are small. So if rho is large, W is approximately 0, okay, and the potential V is approximately 0. This is kind of the thing we want. We have a symmetry under shifts. A goes to A plus now a continuous constant C, okay, to a good approximation. Okay, so the approximation is broken by this e to the minus rho. Okay? And the sort of reasoning that I believe Witten had and that people have applied subsequently is, well, we know there should be things like this, or there, if string theory, for example, or some may, or it does, doesn't actually have to be string theory. It can be some theory with large extra dimensions. It can be various sorts of things. Okay, that if some theory like that describes nature, then we expect that there's some things like this kind of number, this rho might, for example, be the fine structure constant, or 1 over the fine structure constant, or something like that. We know that there should be small numbers. Those small numbers might also be responsible for understanding hierarchies, things of that sort. If there are, so it's plausible, and different people will argue how plausible, that there are such small numbers, and that this might account for a Pacheco symmetry. Okay? So there is certainly some limit of string theory, some region of the moduli space of string theories, for example, which exhibits this kind of approximate Pacheco symmetry. Okay? And so we might hope that this is a setting, okay, which provides a realization of the Pacheco solution to the strong CP problem. Okay. Now this raises some questions, though. Okay? Because certainly if I'm thinking about string theory, okay, then what should this FA be? Okay, well, I don't really know exactly, but FA is probably not 10 to the 11th. So, in fact, a lot of people who build models of this sort and so on will tell you, well, FA is naturally, it's not quite M Planck, it's maybe alpha times M Planck or something like that. Okay, so FA might be something like 10 to the 15 to 10 to the 16 GeV. Okay? And that's problematic from the point of view of this cosmological argument I gave earlier. Okay? I said that FA had to be less than about 10 to the 12 GeV, okay? Not to generate too many of these axions in the early universe. Okay? So how can we reconcile that? Well, okay, we have to think, if we're going to live with that, we have this kind of scale, we need to reconsider our cosmology. Okay. And our Axion cosmology was very much built on the idea that the universe was once extremely hot. Okay? So, but we don't really know that. Okay, so I don't know. What do you think is the highest temperature we know about with any reliability? MEV, yeah, right? So temperatures of order nucleosynthesis. So we don't know much about roughly 10 MEV. Okay. And in fact, I don't know. Well, the status of supersymmetry is certainly questionable at the present time. But for example, if we consider this supersymmetric setting as a model for this phenomena, then we actually have an issue in cosmology associated with this field rho. So in supersymmetry, this field rho, okay, this rho is typically we expect to have mass much greater than the axion mass squared. Okay? And as a result, it also behaves like the axion. It behaves like a scalar field. It's stuck for a while and then it oscillates. It oscillates when h is of order m rho. Okay? And if, for example, if the amplitude of these oscillations is, say, the Planck scale or something like that, then the energy in rho, I've got too many rows here, rho of this modulus, we'll call it, is over, so let's put it modulus, over the axion is of order 10 to the MP, excuse me, over FA squared. Okay? So this thing actually carries much more energy than the axion. It's parametrically a much more serious problem or much more serious issue than the axion. Okay, one has to understand what happened to its energy. And for example, if this modulus, when it decays, okay, it reheats the universe. It effectively dilutes these axions. It sort of restarts the clock. Okay? So and so in particular, okay, people often consider that the possibility that this modulus reheats the universe to a temperature T, in fact, of order this 10 MeV. Okay. And it turns out if you retrace this kind of calculation I did before and you ask what does that mean for the axion, that means that Fa has to be less than or of order, well, I'm being a little generous here, but about 10 to the 15th GeV. If you're really honest, it's about 10 to the 14.6 or something like that. Okay? So one has a sort of different kind of cosmology, okay, in which the universe was never, at least in, as far back as we can look, was never terribly hot. Okay? It was never much hotter than 10 MeV. Okay? And in which the dark matter are still axions, okay, but they're axions which are lighter and more weakly coupled than the axions which are, for example, being searched for by the ADMX experiment. Okay, so this is kind of an alternative cosmology and an alternative picture of axions. Now, of course, this is frustrating. Well, a lot of things here are frustrating. Okay, but this is frustrating from the point of view of detection. Okay, so this is out of reach of, for example, of ADMX, if this is correct. Okay, and what you're going to hear from next week from Peter Graham are some ideas for looking for axions with these kinds of couplings and masses. Okay, so there are ideas, there are proposals for prototype experiments which could possibly see such particles, and they involve different sorts of strategies than this cavity experiment I described before. Okay, so my time's about up. So I think what I'd like to do is I'd like to kind of reprise a little bit what we've done and offer some assessment. So first of all, so what are some things we did? We've described the strong CP problem, and okay, and hopefully some of that was clear. And this is a set of issues that kind of arise all over the place in the standard model and beyond the standard model, in understanding quantum field theory, string theory. Okay, so a lot of these issues are very general, and a lot of the techniques, things like these instanton techniques, okay, recur in a lot of places. Okay, and then we listed these three solutions. Okay, so I talked about these three solutions of the strong CP problem. The mu equals 0, okay, solution, the Nelson bar, and the axion. And I gave them some grades at the beginning. And I'm of a generation that A was the beneficiary of grade inflation and then tended to engage in it later. And so I think I engaged in some grade inflation there, especially in conversations with some of my colleagues about the axion mechanism. I think I got to downgrade things. So I think originally I gave this thing a C. So I decided I've got to downgrade this. So I'm going to give this a D. And this is in the category of things that, hopefully you'll all be famous professors in a few years. And you'll have students come in your office and they'll talk about the unfairness of something. And so there's a caveat here that if you decide that you don't trust the lattice gauge computations, the grade gets a lot better. Okay, so that's in the category of where you get to check on the form that there was an error and you change the grade. Okay, but for now we'll put a D. This one I think I had a B minus. I'm going to put this as a C minus. Okay, so it went down. And I gave you some reasons for that. And basically, this was because you needed to sort of tune scales, okay, and you needed a lot of coincidences. It's just pretty weird. It just doesn't feel generic. And as I said, one of the things I said about the strong CP problem at the start is this is a problem which, no, there's nothing qualitative about nature, without even being anthropic exactly or something. There's nothing qualitative about nature that cares whether theta is, 10 to the minus 9 or 10 to the minus 6 or something like that. Just nothing would change very much. Okay? So things that require really bizarre coincidences and so on. Okay, so I give it a poor grade. Its grade could get better if you could figure out a way to do this more cleverly. Okay, and I think one of the things that some of my conversations with you have gotten me thinking about is, and I've been suggesting to people, is maybe somehow in some cleverer way of embedding this and thinking about flavor symmetry, the origin of quark masses themselves, maybe somehow one could exploit this fact that we talked about, that the radiative corrections to theta in the standard model are so small. Maybe that's telling us something else, but Nelson bar somehow doesn't go far enough. Okay, so again, the grade could be improved if one could do that. Okay, and here, so I'm going to actually downgrade the Axion a bit also. I'm still going to put it at number 1. But, and here this problem, what the problem that troubles me is this problem that I really only talked about briefly, but is the origin of the Chase-Quinn symmetry and the requirement of this high quality. Okay. So I've told you how these two grades could improve. Grades for these two solutions could improve. The grade here might improve in the following way. Okay, so well, first of all, it could improve with a discovery. So that would be spectacular. Okay, so then it gets an A+, and I don't, and the other stuff, who cares? Okay, but another way this might improve is if, what did I want to say? Yeah, another way this might improve. So as I said, I gave it this string theory setting, or this, kind of more general, perhaps higher dimension setting, in which we might understand this small quantity, the quality of the Pacheco-Quinn symmetry is associated with some exponentially small number. Perhaps I'd require to understand something else. So in that period where I was more hopeful about supersymmetry, for example, I would have said, I expect some exponentially small thing like that to account for the hierarchy, and maybe I need that squared, or somehow that will enter some other place, and that will, as some kind of accident, give rise to the Axion. Okay? So if you could figure out a way to do that, you can also improve the grade. Okay? And in the spirit of this school, okay, maybe we're just missing something. So I'll just put a question mark here. Okay, and I think with that, and I know some of this has been a little quick, but I hope that you've been left with enough exercises that you can fill in all the gaps. I will post the rest of the notes from the first 2 lectures are posted, and I'll post the third later today or early tomorrow. Okay, and I want to thank you for your attention, and I'm sorry I ran 5 minutes over.